Okay, now here we have the case of a horizontal rectangular plate. We're going to call this depth right here h, and here it's quite simple. We're looking for the pressure on this plate. The pressure distribution is just a rectangle. And you can probably figure out yourself what the equation is for the pressure on that plate. But it's just going to be P equals rho G H plus P sub 0 if we're considering P sub 0. And therefore the force of the resultant is equal to P times A, and that resultant is going to act at the centroid, which is located right there in the middle. The depth to where it acts is obvious, it's just h because this is not an inclined surface. Now in this case we have vertical rectangular plates, and I'm going to go through two example cases. The first of which is where the plate extends to the surface, which is on the right. You can see this black line right here extends all the way to the surface of the fluid. And that's going to be a quite simple case because we will have a triangular pressure distribution, and triangles are easier to work with than over on the left side where we have a submerged rectangular plate. And here we have a pressure distribution to the surface here, but we're only caring about what's happening on the plate itself, and so we have a trapezoidal pressure distribution over on the left side. We don't care what's happening in this top section right here. So if we want to look at where the resultant is here, if we're trying to find the magnitude of the force, again we're going to do that at the centroid of the plate. If we try to figure that out here, which is half the depth, just like in the last case, we have an equal amount under and over on both sides. So just as in the general case, we have that the force equals P average times A, and P average is going to equal rho G Y sub C plus P sub 0, and my P average, my Y sub C here in this case is just going to be my total depth, which I'm going to define here as h. Y sub c is just going to equal h over 2. Now on the left side, it's a little bit more complicated. I still will calculate that force in the same way, where F equals P average A, but it's at the average depth of this submerged plate. So I'm going to define this distance as h1 and this distance as h2. And so now my y sub c is going to equal h1 plus h2 divided by 2. And my P average is still the same. P average equals rho G Y sub C plus P0. Where these differ is more significantly is in the calculation of where this arrow acts. On the right side, we introduced just the relationship that this distance y sub p, so if we're going to look at where the arrow is actually going to act, and we're going to call that y sub p, then we can say that y sub p equals 2/3 h. Easy relationship, but it only applies when this vertical surface is in contact with the surface of the water, as it is here. If the whole plate is submerged, as it is here, we don't have a triangle, and so we can't use this relationship. Over here on the left side, the y sub p equation is more complicated. You're always safe if you use the equation for the general case that we talked about earlier, which was y sub p equals y sub c plus I x sub c over a y sub c. We also introduced a equation that you can use. Once again, we've got where this arrow acts, and we're going to call that y sub p over here. And you can just use that y sub p equals 2/3, not just h, but h1 plus h2 minus h1 h2 over h1 plus h2. You can use this equation when you have this submerged plate. Incidentally, over on the right side, if you refer to this h over here as h sub 2 and h sub 1 would just be 0 in this case, since it extends all the way to the surface, you can see that this would be 2/3 times just h sub 2. The rest of this would go away, and you would have this same relationship on the right side. So that's it. Those are the most important things. In the last video, I will just briefly review how to address fluid statics on a curved surface.